Hi, my name is Mark Turner, and this is a video tutorial I prepared for edX course 6002X, Circuits and Electronics, taught by MIT professor Anand Agarwal. In this tutorial, we'll be designing and building a digital to analog converter using a resistor ladder and an op-amp. I hope you enjoy it. We'll start by solving the first part of problem 15.6 in the textbook, which will introduce the concepts we'll be using later. This problem wants you to generate the weighted sum of two inputs according to this equation. We'll use superposition to deal with each input separately. Notice that when we short out V2, V1 sees a voltage divider consisting of R1 and R2. And the output presented here is V1 times R2 over R1 plus R2. Similarly, when we short out V1, V2 sees the same voltage divider but in the opposite direction. The output presented by V2 here is V2 times R1 over R1 plus R2. Since the sum of the resistances is common to the denominator of both dividers, it doesn't complicate the math, and we'll ignore it for the minute. So a solution for the weighted sum would be R2 equals 3 to give R1 the weight, V1 the weight we want. R1 equals 5 to give V2 the weight we want. Then the value presented here is V1 times 3 over 8 plus V2 times 5 over 8. But we don't want 3/8 or 5/8. That's where the op-amp comes in. This is a standard non-inverting op-amp configuration, so the gain is RA plus RB over RB. We want that to be equal to 8, and it should be clear that 7 plus 1 over 1 will work. So RA is 7 and RB is 1. All done. Well, what does a weighted sum have to do with a digital to analog converter? Let's look at the function of a D to A. It takes some number of digital inputs representing a binary number. Since each one is a binary input, the value of each is either logic 1 or logic 0, nothing in between. The actual voltage value of logic 1 is not important yet. It's determined by the device that's generating the inputs. I'm assuming it's some small positive voltage. However, in everything that I do here, I'm assuming that logic 0 is actually 0 volts, that is ground. The analog output that I want to generate from these digital inputs is VO is proportional to 2 to the n times dn, the input dn, plus 2 to the n minus 1 times dn minus 1, plus 2 to the 1 times d1 plus 2 to the 0 times d0. So you see it's a weighted sum. Each input has twice the weight of the next one down. There's an issue of scaling that has to do with the actual value of logic 1 and the range of analog values that we want to generate, but we'll deal with that later. Let's concentrate on the weighted sum first. We'll start with two inputs to our D to A like we did in problem 15.6. The upper input is the more significant bit, so we want it to have twice the weight of the lower input. So we'll give the lower resistor a value of 2, since that impacts the weight given to the first input in the voltage divider, and we'll give the upper resistor a value of 1. That was easy, but 2 bits of input is pretty boring. Let's add some more. Well, now things are suddenly messy. When we look at a single input in isolation, the voltage divider has become 1 resistor in series with 3 resistors in parallel. I'll confess when I first looked at this, I wasn't sure how to solve it, but I made a guess and then proved that my guess was correct. The guess, which I'm sure you've all made by now, is to make this third resistor half the value of the one below, and the top one half of that. And to make the math easier, I'm going to readjust all the values and assign them the values of 8, 4, 2, and 1. Let's prove that this is correct. By now you should all be thinking, when you see a bunch of resistors in parallel, formulate the problem in terms of conductance. Let's quickly review the voltage divider relation in terms of resistance and conductance. The voltage at the intermediate point here is Vs times Rb over Ra plus Rb in terms of resistance, and it's Vs times Ga over Ga plus Gb in terms of conductance. And remember that the conductance of a bunch of resistors in parallel is simply the sum of the individual conductances. Back to our D to A. I've filled in the assigned resistance values and their corresponding conductance values. Of course, in a real design, you wouldn't use resistances that small. You should multiply them all by 1,000 or even 10,000. Using superposition, let's look at just one of the digital inputs. Using the voltage divider relation, the voltage presented here by this input is the upper conductance, 8/8, divided by the sum of the upper conductance and the lower conductance. And the lower conductance is all these resistors in parallel, and that's simply the sum of their conductances. So the denominator in our voltage divider is just the sum of all the conductances in the entire resistor ladder. And that comes to 8, 4, 2, 1, 15/8. In fact, this same denominator is common to all of the voltage divider relations for every input. So the scaling of each input is determined solely by its upper resistor. So the voltage contributed by the most significant bit is its conductance, 8/8, divided by the sum of the conductances, which is 15/8, for a final value of 8/15. So we'll put the contribution here as D3 times 8/15. Similarly, the contributions of the other inputs are D2 times 4/15, D1 times 2/15, and D0 times 1/15. Note that if all the inputs are on, that is, each has the value of logic 1, then the sum at the output is 15/15 times logic 1. In other words, when all the inputs are asserted, the entire value of logic 1, whatever that is presented at the output here. Remember, I'm assuming that logic 0 is 0 volts. It's no coincidence that a 4-bit binary value of all ones is equivalent to decimal 15. Notice that we're still ignoring the op-amp, which is there to scale from logic 1, which we've seen as the largest value I can express with my digital inputs, to some analog value that is suitable for my purposes. In other words, what I do with the op-amp is completely dependent on the target design. So let's build something. Here I have an Arduino with 4 digital outputs, which I'm treating as a 4-digit binary number, and I'm running a simple program that has these 4 outputs continuously counting from 0 to 8. I've connected them to 4 LEDs so you can see what's happening. In order to do the scaling of the output, I'll need to know what logic 1 is on the Arduino, so let's measure that. I have a constant logic 1 at this output here. I was hoping for a friendlier number, but we can deal with this. While we're at it, let's see what logic 0 is on the Arduino. Remember, I said I was counting on that to be 0. Well, it's not exactly 0, but we'll forge ahead anyway. All of these measurements are made with respect to what is essentially ground on the output amplifier, that is, the center point between the positive and negative supplies. I'm using the same ground for the Arduino. Here I have the circuit we just designed doing a weighted sum of 4 inputs. In this actual implementation, I'm using resistance values of 10K, 20K, 40K, and 80K. Notice that I had to implement the 40K and 80K with resistor pairs, since those aren't standard values in the E24 series of resistors that I have available. Here we have the venerable 741 op-amp. The output of the resistor ladder comes into V+ here, And here's the feedback voltage divider off the output, with the feedback going to V-. The question I've been putting off is, what is the gain to implement in the op-amp circuit? We've seen the value of logic 1 coming in, so let's decide what we want to do with the output. Let's say I want the output to be as many volts as the binary value at the input indicates. So if my digital input is binary for 5, I want to see 5 volts out. If it's 2, I want to see 2 volts. Well, we know that the maximum value I can express at the input is all ones, or 15 decimal, and what that generates at the output of the resistor ladder is the value of logic 1, which we've seen as 5.05 volts. So the gain we want in the amplifier is something that will convert 5.05 volts to 15 volts. I already calculated the appropriate resistor values for the feedback divider. Let's plug in the digital outputs from the Arduino. The Arduino is still counting from 0 to 8 on those 4 pins. What we should see at the output of the op-amp is values ranging from 0 to 8 volts, which is what we see on the multimeter here. It's not perfect, but it's pretty good. I want to mention that the reason I only counted up to 8 instead of 15 is because I'm using 9-volt batteries to power the op-amp, so I can't really realistically expect to get much more than 8 volts out of it. But I did want to show you at least 4 bits. After finishing a project, it's a good idea to review what you might do differently next time. There are 3 areas of improvement I'd like to call attention to. The first is in the output stage. It's inconvenient to have to compute and set up scaling for the output amplifier. Commercially available D/A's take a reference voltage, which is the voltage you want to see for full-scale input. Then the D/A outputs a value somewhere between ground and the reference voltage, proportional to the binary input. The second comment has to do with the precision of the resistor ladder. The metal film resistors I used have 1% precision, but if I had 8 bits of input instead of 4, that would mean that a 1% error in the most significant bit would have the same weight as the entire least significant bit. This is difficult to address with discrete components. The third and most important area for improvement has to do with the input stage. This converter shouldn't have to know the value of incoming logic 1 and logic 0. Instead, it should implement the static discipline and implement reasonable values for VIL and VIH that the downstream device can handle. Then it should condition the inputs internally to have the appropriate voltage levels for the rest of the circuit. We'll address that in the next tutorial. In this tutorial, we've seen how to build a digital to analog converter using a binary weighted sum of inputs, and then use an op-amp to scale the output to some value useful to our design. I hope you enjoyed watching it as much as I enjoyed making it.